All right, we're back, still in section 2.2. We had just gotten the definition of a limit and some mathematical notation for that. Now that we know the definition and notation, we can look at some quick limits with some really basic little graphs. All right, so quick example here. Let's think about the limit as x approaches 5 of the function x. Okay, and we'll see if we can figure out what that equals. All right, now let's make a really quick little graph here. Okay, notice that our function is just x, so, and maybe I shouldn't use an arrow for that because arrows mean special things in the limit notation. I'll use a different color so we know it's something different. F of x equals x, there we go. Okay, let's draw the graph of f of x equals x really quickly. Hopefully we know that that is just a basic line, slope of 1 going through the origin. Boop, like that. Okay, there's f of x equals x. And we want to see what happens when the x values are approaching 5. So we want x to get real close to 5. Let's put 5 on our little graph here. 1, 2, 3, 4, 5. 5. Okay, and 1, 2, 3, 4, 5. 1, 2, 3. Okay. All right. So as the x values get closer and closer to 5, coming in towards 5 from both directions, we need to see what's happening with the function values themselves, all right? The f of x values, these guys. Okay, so as we come in along the x direction towards 5, that would be, okay, imagine putting your fingers on the function. Okay, so put your fingers like here and here, and then move your fingers toward one another to simulate what's happening as x gets close to 5. So both your fingers are moving towards an x value of 5 horizontally, but they're scooting along the function itself. So your fingers are doing something like this. Let me zoom in a little bit so we can see that in more detail. Okay, so yeah, we want fingers on those 2 dots, and then horizontally you're moving in towards x equals 5, but you're tracing along the function itself. Okay, because that's showing you what's happening with the y values or the f of x values. Okay, so you're coming in this way, and as we get closer and closer to x equals 5, the y values are also getting closer and closer to 5. It's just 5 on the f of x direction for that. Okay, so you're moving in towards x equals 5, your y values are moving in towards 5. So the limit as x approaches 5 of the function x actually just equals 5, because that's the y value that we were getting close to. Okay, well, let's do another kind of quick limit here with a little graph. All right, look at the limit as x approaches -20, and our function f of x just equals 3. Okay, and we are going to find that limit. All right, so yeah, let's make a little note here. That is the function we're working with, f of x equals 3, and we'll use the same type of approach here just to make a quick little graph and see what's going on. Okay, So we want to get our x values close to negative 20. All right, f of x here. All right, the function f of x equals 3, if you'll recall, that is just a horizontal line. All right, so 1, 2, 3. Okay, horizontal line, just like that. Okay, it's a constant function all the way across. And yeah, we want to see what happens as x gets close to negative 20. I'm just going to say this is negative 10, and then this here is negative 20, just to make our x-axis a little more compact there. Okay, so let's zoom in on this and see what's happening. So you can use the same type of trick here. We want our x values to approach negative 20, and we want to come in from both sides and see what's going on. So we want to come in toward negative 20 horizontally, okay? So you can use this trick again. This is a legitimate trick to put your fingers on the actual function and then horizontally move towards the x value you want while keeping your fingers on the function graph. Okay, so you might put a finger like here and here, and then you're gonna bring those fingers horizontally closer together, moving in towards x equals negative 20, like the arrows down below show. But you're going to keep your fingers on that black line of the function. Okay, so you're keeping your fingers on here, but moving in towards x equals negative 20. You move them in, and you see that the y value that we're approaching is still at 3. Okay? That's an actual point on the graph. As x goes toward negative 20, the y value goes toward 3. It's actually consistently a y value of 3 all the way across, but even as we're getting close to negative 20, our y value is 3. Okay, so that is our limit. All right, it's the y value that we were approaching right here. Okay, so there we go. On this particular graph, it turns out whatever x value we were approaching, the limit still would have been 3. Since it's a constant function, the y values are only really approaching that one value. So kind of tricky in how simple the function is. It can make you overthink the problem sometimes. All right, but the idea is that concept of tracing along the function, looking at what the y values do as the x values get closer to whatever value was specified. Okay, so let's take a little look here at a note, a good note for looking at these functions, especially with graphs. All right. And our note is that the function itself, f of x, doesn't necessarily have to be defined at the value that we're interested in. So defined at x equals c from our definition. And we could have some other scenarios here. We could have a limit. Okay, so we could have a limit as x approaches c of f of x that equals L. Okay, but if the function is defined at c, the value of the function when you actually plug c in could be something different than the limit. Okay, so that is kind of notation heavy there. Let's take a look at some pictures, some graphs here to see what that note is really saying. All right, so on our first graph here, we are going to set up a limit that looks like this. The limit where x approaches c of some function f of x, it equals L. All right. So let's say, let me make some generic function here. I don't like that one. All right, let's say that's our function. Okay, this is f of x. Okay, yours might look a little different. That's fine. We roll with it. Okay, so that's the function. Let's say this is our value c that we want our x values to get close to. And so we can even find the limit like we were doing on those previous graphs. All right, we're going to get closer and closer to x equals c, coming in from both directions. Put your fingers on that function curve and horizontally move them closer and closer together, approaching x equals c, and see where the y values go. All right, that would be right here. So that is our limit. Okay, cool. So the limit L would be this guy right here. Change back to the normal color. All right, so there's our limit L. And we've drawn a solid function here, okay? The function f of x doesn't have a hole in it. It's actually defined at c, x equals c. There is a point there. And the point, the value f of c actually equals L. So this function is defined at x equals c, and also f of c equals L. All right. Now, let's say we draw a very similar function. I'll do my best to make it look similar. But when we get close to that c value, which was somewhere around here, I'm going to say that this function is actually undefined at c. It's got a hole in the graph now. Okay, it's almost the same function, but not quite. Now the thing about this, if you think back to our very first example from this section, you can still find a limit even if the function is undefined at the x value that you care about. Over here in that first example, we were letting x approach 2. The function was undefined at 2, but we were still able to find the limit, the y value. F of x was approaching 12. So you can still have a limit even if the function is undefined. And that's actually what we have here in this second graph. It's the same limit, all right, as we're moving in towards x equals c. When we trace along the function, it's still approaching that same y value. It's just that when we actually get to x equals c, there's a hole there instead of an actual point. But we were still approaching the same thing. It's what happens in the approach, not what happens at the actual point itself. Okay, so this is undefined at x equals c. And so we can't say anything about f of c. It's undefined. F of c doesn't exist. Okay, there is no point there. All right, now for the third case, we're gonna do another similar type of thing. All right, let's get our little setup here. There's our value C. Here's our function, basically the same coming in. All right, let me make it look similar. Okay, oh, the L value was there. Okay, we're gonna put a hole in the function again. All right, like so. But then we're going to say that there is an actual value for f of c. It's just not in that hole. Let's say f of c is defined as being some other point, like up here. All right, when you plug c in, you get this actual y value, f of c. But the limit L is still down here in the same spot that it has been, okay? So we're approaching x equals c from both sides. We put our fingers on the function and we trace in along the curve of that function. And where it looks like we're going, what it looks like we're approaching, is still this value L, okay? That's where it looks like the function is going. Sure, yeah, at the actual point, the function decides to pull a fast one and surprise us by throwing a point up here, but the thing that we were approaching is still that same value L, okay? So this has a defined value for f of c. So f of c actually exists, but f of c doesn't equal L. All right, so the thing about all three of these graphs is that they all have the same L value, even though different things are happening at the point where x actually equals c. All three of these have the same limit. So all three graphs or functions, all three of these have the same limit. All right, the limit as x approaches c of f of x for all three of those f of x's, it equals L on all three of those. Okay, so interesting. All right, now in the next video, we'll look at some kind of unique functions, see if we can put this limit idea to work here.